Okay. So I'll give everybody a moment to attempt this. Remember, you would be allowed to use your calculator on the exam. So here we know the -1 is all being squared, so that would make it a +1. Now 3 times -1 is a -3. Subtracting a -3 becomes positive, so we get 5 plus 3 plus 7. So did y'all get 15 is the answer? Now continuing, if y'all would attempt this next one. Everywhere there's a y, we replace a -3. Everywhere there's an x, we replace it with a 2, and then we simplify. And I believe we should get -36 as our answer. Yes, Luke. Next, we'll simplify. So we'll distribute, combine like terms. Give everybody a minute to attempt it on their own. So we had 5 x's, we subtracted 6, so that should leave us with -1x plus 5y plus 7. Now for practice, I'm going to write a very similar problem for us. If y'all would complete this problem, look at why it's related to our last example, and then we'll carefully see why we get a different answer. John, does it make sense in this new example? The only difference is that the 6x plus 7 is offset in parentheses. So the minus needs to distribute not only to the 6x, but also to the 7. Whereas here, the minus only went to the 6x. So if y'all would simplify that. Now we know if we're looking at terms that have x's but x squareds, we treat x's and x squareds differently. So I'll give everybody a moment if y'all would distribute and combine like terms here. So we should get 2x plus 2x squared minus 5x squared minus x. The x squareds combine together as the 2x's. So did y'all find x minus 3x squared? Okay. Okay, now here we have to completely simplify this expression. We notice the first two terms are fine, but in order to combine like terms, we first need to distribute the -4 throughout. We had 7x squared, so we took away 4 of them, so we were left with 3x squareds. We had 10 x's, we added 12 of them, so we should be left with 22 x's minus 28. Now this brings us to 6.2 material. In 6.1, we simplified expressions, but in 6.2, we learned how to solve equations. So if y'all would solve one equation, what x value makes 2 times x equal to -10? Now, when it comes to solving equations, we think in terms of the pairs of ideas. So like multiply and its opposite divide, add and its opposite subtract. So since these 2 and the x are currently being multiplied, if I was to try to get x by itself and solve for this, I'd have to do the opposite and divide both sides. What's done to one side must be done to the other. 2 over 2 cancels to give you 1, so we just have a single x equals -5. And now as we turn our attention to equations that have a bit more to it, we see in order to get x by itself, I would have to move the added 20 and move the multiplied by 7. Now, technically, it doesn't matter which one you do first, but in practicality, you want to move what's farthest away from the x first, because if you try to move the 7 first, you'll be likely to make a mistake. So I would encourage everybody to always undo addition before you worry about multiplication or division. So the 20 is being added, we're going to subtract it from both sides. Cancels there. 7x equals -28. Divide both sides by 7, because the 7 is being multiplied by x. And we should get x is equal to -4. If y'all would similarly solve this one, remember to distribute first and then solve. Or I guess you don't have to distribute first. You could also get rid of the multiply by 20. I think in this case, dividing both sides by 20 was more efficient. However, we could have done an alternate solution. We could have first distributed the 20 throughout, so 20x plus 100 and 20, or sorry, plus 40. 20 times 2 equals 100. And once we distributed the 20, then we could have solved. So if you prefer this method, then you would subtract 40 from both sides. 20x equals 60, divide both sides by 20, and we still get our answer of 3. So just a preference on which we do first. Now in this problem, we focus on the fact that there's a variable on each side. So our strategy here will be to move all the variables to one side, numbers to the other, then solve. Any questions so far? Now next step here, we see that there's variables on both sides. And while I might think of dividing both sides by 3 first, does everybody agree that 4 and 3 doesn't divide well? So I think in this case, while sometimes that's a good strategy, if it would divide easily, here it doesn't. So I think I would distribute first and then worry about moving all the variables to one side, all the numbers to the other. Now here we see we have a variable on each side of the equation. However, this one is kind of being hidden. We need to distribute first and then combine like terms to see what's actually happening on the left side. Once we fully simplify the left side, then we'll try to move all the variables to one side, all the numbers to the other. that match what everybody found? Now next up, we look at the equation. The left side is perfectly simplified, but we know we need to simplify the right side before we can begin to solve. So let's simplify this and then solve. So nicely, as we were solving this one, we saw that the positive 10 got canceled with the negative 10. So the constant terms dropped out. Now we also had some type of equations where the answer wasn't a single x value, but based on how it was described, you would have to answer whether there was no solution or infinitely many. Now remember, there's going to be no solution if whenever you simplify things, you end up with a false statement. And it will be infinitely many solutions if when you simplify things, you end up with a true statement that does not depend on x. So something like 2 equals 2, 3 equals 3. A false statement would be something like 1 equals 2. So if y'all would simplify and solve this expression and see whether we end up with a false statement or a true statement not dependent on x. The x's to one side, so I'm going to subtract 6x from both sides. Now as I do, it cancels it here, which was my goal, but do we see since there was exactly 6x on the other side, it cancels it here as well. So we'd be left with 3 equals 10. False or true? Definitely false, so we'd end up saying there's no solution. The two things should have never been set equal to each other in the first place. You would similarly consider this one. Now we might notice right off the top of the bat that whenever we distribute, we get exactly the same thing on the other side. That's a hallmark for being infinitely many solutions because they're actually the same thing, just slightly disguised. Whenever we subtract 10 from both sides to move the 10x over, the x terms cancel each other, and we're just left with the true statement 4 equals 4. So we'd say there are infinitely many solutions to this equation. Okay, now that brings us to 6.3. In 6.3, our focus was either working with maybe some percentage problems or word problems, writing equations based on the verbal descriptions and then solving for the answer. So first up, we're asked if a number is decreased 45%, the result is 110. What was the original number? Give everybody a moment to attempt this, and then we'll discuss it. Now, I'd say there's a few things that we want to be cautious about here. First of all, if I'm decreasing by 45%, I'm not looking for 45% of some number. Instead, think about when you're decreasing by 45, always change it into the phrase of, well, how much is left? So we originally had 100%. And if we took away 45%, we would have 55% left. So 100, the total 100 minus 45 equals 55% of original. Now, whenever we take 55% of the original price, the result is 110. So we're not taking 55% of 110. That's the result after we took 55% of the original. Now, before we go forward, does it make sense why we had to translate this decrease by 45% to immediately take away from the whole? Because if you've got a 45% decrease, you're still paying 55% of the sticker price. If I had a 30% decrease, how much of the original would I still have to pay for? 70, right? Good. Now, at this point, we know to find the percentage of a number, this has a very set procedure. Let's call our original price P. Then to find the percentage of a number, you change the percentage to a decimal by moving the decimal place over twice, and then multiply it by the number that you care about. So in our case, by P, the result will be 110. So now we've set up an equation that we can solve. We'll divide both sides by 0.55. And we should get 200 back as the result. So the original price is 200. As expected, the original price should be higher than the discounted price. So that kind of makes consistent sense. So remember, if you're told it's a decrease, you need to subtract that number from 100 to get the actual percentage that you're taking from the original. How would this problem have changed if we had said increased? Then instead of subtracting 45, you'd add 45. And you'd figure out what is 145% of the original, which you move the decimal place over. That would be 1.45, etc. So if it decreases, you subtract the percentage from 100 to figure out the percentage we have of the original. But if it increases, you add that percentage to 100. Good for that problem? Okay. Now, I've collected a few word problems just because of time. We're not going to go over all the different types that we covered, but if you'd like to remember, you can look at our 6.3 notes or our 6.3 lecture video to go over additional problems. If y'all would read through this one. So we have, in the beginning when we started measuring, the average age was 12 years. For the period given, we know that it's increasing, so we need to think it's growing, specifically by 0.1 years per year that passes, so 0.1 year of the average. If this trend continues, how many years after 2014 will the average age be 13.1? So we could set up a idea, let's say T is our time since 2014, because that seems to be how they're describing things. Remember, with these problems, if you're not getting traction, the first thing you'd want to ask yourself is, have I labeled the variables? And the variables are whatever quantities are changing. So here, time is passing since 2014. And as time passes since 2014, the average age of the vehicle is increasing. So maybe I could call A the average age of car. Now that I have these variables, I can express the relationship. For this problem, we've got a starting point, and then we've got a yearly growth. That makes us think of a linear equation. So the age is equal to this yearly growth, 0.1 times however many years passes, plus the starting point of 12. And now I need to think, okay, they gave us one piece of information. Is this 13.1, is it an average age, or is it a year since 2014? Because that will determine whether we plug it in for A or T. Do y'all agree it's a age? So since they gave us an age, we plug that in for the age, and we get 13.1 equals 0.1 T plus 12. And at this point, this becomes a problem like we just did a lot of them. We're solving the equation for T. Did y'all get T is 11 years since 2014? So next up, let's work on question 4. And the phrase depreciating means losing. So it starts off at $24,000. Each of the year it loses T. This is our value over time. $10,000 is a value, so we set that equal to the value that we have. And we should get 7 years. see through our next question. So both of these deal with the cost. In company A, we start with the fixed rate of $16 plus, let's say H is hours. So every hour we charge another $8. Company B has a cost of a larger upfront cost, $40, but the hourly charge is significantly less, only $2 per hour. Now, when they ask us when will the cost for each company be the same, they're asking us to set these equations equal to each other because we want to know when the costs are equal. So we get 16 plus 8H equals 40 plus 2H. And now we move the H's to one side, numbers to the other. And we get that their price would be the same after 3 hours. Now that was just a sampling of 6.3. Like I said, if you'd like more practice working with these word problems, I'd encourage you to go back to the 6.3 lecture video. That's in our class YouTube playlist. So now let's move to inequalities. As a reminder for inequalities, remember that the tinier part of the angle is pointing to the smaller number. The larger point of the angle is pointing to the larger number. So because of that, I know I can read this as x is smaller than or equal to 5. Think about how you'd say this one. X is greater than -10. Now, when they ask us to graph, that means we have our number line. We place the value of interest. So in the first case is 5. In the second case is -10. And we see that just placing that value splits our number line into values before, at, and after. And we want to shade whichever part is described by the inequality. So when it says x is less than or equal to 5, think about which one of these sections have you less than 5. Do you agree that would be to the left? And now the or equal to, remember that means you have a solid circle at the 5, and then you're shading less than. Had it just said less than 5, we would do an open circle. So if y'all would similarly shade for x is greater than -10. So for greater, we want to be to the right. So we're going to do an open circle because it's not or equal to. And then we'll shade to the right of 10. -10. So that's just representing the graph of the inequality. We also had inequalities that we had to simplify first before we could graph, and we very much used the same skills that y'all did for solving equations. The one thing to remember is if your solution ever has you multiply or divide by a negative number, you have to immediately switch the direction of the sign. So if everybody would work on this next one. We get x by itself, so we'll subtract 3 from both sides. 1 minus 3 is negative 2. Now, would you all agree to get x by itself, I'm going to have to divide both sides by a negative 1 because it's currently negative. Or I could also equivalently multiply by negative 1 in this case. Now, when I do that, since there's an inequality, the first thing I do is I switch the direction. It stays equal to because it was originally equal to, but instead of being a less, I'll need a greater symbol. So write that first. And we get that x should be greater than or equal to 2. We have 2. Since it's or equal to, we do a solid circle. And then we want to be greater than, so we shade to the right. So do remember, for inequalities, if you're ever multiplying or dividing by a negative number, you do immediately have to switch the sign to the opposite direction. Let's solve the next one as well. And then graph the solution set. Here we'll divide both sides by 10. X is greater than or equal to 3. 3. Or equal to solid, and then greater than, we're shading to the right. Now do remember on these ones, as you take the exam over, or the final exam of these problems, when you see these problems, that you'd want to pay attention to slight details, because definitely this would also be an option, right? We wouldn't want to mistake that. And we could also have the option this, which is almost correct, right? Except it doesn't have the solid circle. So as you're selecting from the answer choices for these problems, do really look at the details. Let's attempt these two. We need to simplify the expression, and then we can graph it. So x should be greater than or equal to 5. Now our next one includes a fraction. And my reminder to everybody, anytime there's a fraction involved in the equation or inequality, is to figure out what could I multiply each side by to get rid of the fraction. So here we see the only fraction is a 6. So if I multiply both sides by 6, it will clear the fraction. What's done to one side must be done to the other. And then we get the statement x should be less than or equal to 12. So now we get to inequalities where we've got x's on different sides. So we know we still follow the same strategy, x's to one side, numbers to the other, with the only caveat that if we ever multiply or divide by a negative number, we would have to switch the direction of the sign. It's just greater than, so we clearly make an open circle around 1. X should be greater than 1, so we should shade to the right. So x should be greater than or equal to 2. Then we would look at our next one. So here we're multiplying by -2. So if I want to get x by itself, I'll have to divide. But since I'm working with inequalities, immediately I'm reminding myself, okay, if I multiply or divide by inequality, the direction of the sign has to switch immediately. So before I write anything else, I just immediately switch the direction. Now remember, if it started equal, it stays equal. The only switch is for the switching of the inequality angle. So I've switched that first, so that's good. Now the -2's cancel and they just leave you with the x on this side. -8 divided by -4 is a +4. Now this inequality looks a bit more complicated just because the left side isn't simplified, the right side isn't simplified. So our strategy here would be to simplify both sides separately first. Once they're fully simplified and we combine like terms, then we start to move all the x's to one side, all the numbers to the other. So as you work on this, distribute this first, combine like terms, distribute this, and then work to move all x's to one side, numbers to the other. Now that we've simplified, we can start solving this as we normally would. Now, negative 10 over 8 doesn't simplify nicely to an integer, but we could just leave it on our number line as negative 10 over 8. The little point is pointing to the x, so x is smaller than negative 10 over 8. Open circle because it's not or equals, and then we'll shade to the left. Now this next one looks particularly challenging, and it would be if we left things as fractions. So whenever there's lots of fractions, the first step is in our mind to get rid of the fractions, and you do that by multiplying by a carefully chosen number. And we want to multiply by a number that is kind of the least common multiple between the available denominators or bottom of the fraction. So let's look. I've got a 2, I've got a 6, a 4, and a 3. 12, very good. Exactly right. Do we see 12? 2 divides into 12, 6 divides into 12, 4 divides into 12, 3 divides into 12. Could we have also used 24? Yeah, but if we find the smallest such one, it's just going to make the simplification easier. So as it was very correctly stated, we're going to multiply everything by 12. And when you do so, these fractions should simplify because we chose the least common multiple. So if we'll distribute and simplify, so here we had 12 x's divided by 2. Do you all agree that would be 6 x's? Next, we had 12 ones divided by 6. So 12 divided by 6 is a positive 2. I'm not quite sure why I wrote 24 here. Do we see that would be a problem? So this was a big error on accident. What you multiply on one side, you do have to multiply on the other side, so that should have been 12. Does that make sense to everyone? Okay, so that was an error. We fixed it. So now 12 x's divided by 4 gives you 3. 12 divided by 3 gives you 4. So by multiplying by this least common multiple of the denominators, we now have an inequality that we're more used to working with. We got rid of the fractions. Now, we also had some inequalities where it wasn't just x had to be related to this one thing, it was actually kind of bounding it below and above. So whatever x is, x plus 2 needs to keep you between 5 and 13. So if we want to solve this inequality, it's the same idea, except now when we subtract 2, we don't just subtract it from 2 places. Since there's 3 parts of the inequality, we subtract it from all 3 parts. So 5 minus 2 is 3. X plus 2 minus 2, the 2's cancel, and we're just left with x. 13 minus 2 is 11. And now as we draw this on our number line, we need to plot the points that are important, 3 and 11. For both of these, they're both less than, not or equal to, so we do an open circle. And then in words, does it make sense that x needs to be greater than 3, but at the same time smaller than 11? So see that the number line is split into 3 pieces, this piece, and this piece. Think of which of those 3 pieces actually have us being greater than 3 while at the same time less than 11. That's where we'll shade. Draw a gray with shading in this middle section. So remember, if there's multiple terms, that's no problem. Just remember what you do to one term has to be done to all the terms. So let's similarly work on this one. Now, as I graph this, I want to pay attention to the inequalities. The 2 is just less than, so we do open. The 5 is or equal to, so we have to do that one solid. And then it's saying pick the interval where x is at the same time greater than 2, but less than 5. So that should be here. Now, I believe this is our last one here. Now, as we begin to solve this inequality, do you all see that we do have this 1/3 here? So if we want to get rid of the 1/3, we might multiply everything by 3. So this would have to be multiplied by 3. This would have to be multiplied by 3. It would distribute. And this would have to be multiplied by 3. Now remember, negative numbers are to the left of 0, so -9 is to the left. 0 is over here. Both of these are or equal to, so we do solid. And then x should be greater than -9, so to the right of -9, but at the same time less than 0, so to the left of 0. And that would get us this section. That brings us to the end of our chapter 6 review.